Okay, scary graph, find its equation. It's either going to be a cosecant or secant. What I like to do is think about these as in terms of sine and cosine using their reciprocal functions. It's the best way, I think, for me to remember which one is which. So let's get some basic sketches of what our sine graph looks like and cosine, because usually students remember that pretty, I wouldn't say easily, but sine starts at the origin, goes up, comes back down, ends at the origin. Cosine starts up here, comes down, comes back up, ends at the top. All right, is basically the general sketch of that. Now, wherever sine or cosine have x-intercepts, for the cosecant or secant, depending on which one you're looking at, you get a vertical asymptote. So for each one of those x-intercepts, you get a vertical asymptote. Over here with the secant graph, vertical asymptotes going on there. And then remember, there's this reciprocal relationship, so they always share this highest point in common, right? What would be the highest point on sine is the lowest point of kind of this loop going on with our cosecant graph. Same thing, this lowest point becomes kind of the highest point on this loop. And then similarly over here on the secant graph, match up those highest or lowest points, and they get mirrored the opposite direction. So what's in orange over there is kind of the basic shapes of secant and cosecant respectively. All right, so picking out which one to use. We're allowed to use either one. The easier of these two is probably going to be the cosecant, based on what the graph looks like on the left-hand side, that it looks like we have this nice vertical asymptote going on here at the y-axis, which is what is going on with the cosecant graph. So it wouldn't require a horizontal shift left or right. Now I'll show you how to use the secant graph if you want to use that horizontal shift. But it looks to me like we have vertical asymptotes kind of going on. It's tough to see over on the right-hand side, but it looks like all the way out there at 6. So kind of begins at 0 and ends at 6 before it would start repeating itself because it is a periodic function. So with that in mind, let's kind of set this up for cosecant initially, and I'll tell you how to do secant in a little bit. So it's going to be a times cosecant of b times x. And I'm leaving off a c in the middle here because we said there wasn't going to be any horizontal shift. All right, for the cosecant graph. We'll include it for the secant graph in just a little bit. So we can start kind of wherever we want on this. I'm going to say, let's start with finding b. All right, we can find a or d. We're going to find them all in a second anyway. But basically, this has to do with the period. The period of our graph is calculated by the original period of the cosecant graph divided by whatever b is. Okay, so let's figure out what's the period of our graph to begin with. I'm going to say we're starting right here at the y-axis, so an x value of 0, and we're ending all the way out here at 6. So I would say our period of our graph is 6. Now, what's the original period of cosecant? Well, it typically starts at 0 and ends at 2 pi, just like sine does. All right, so the original period there is 2 pi. But we have to divide that by b. Well, now we have an equation where we don't know what b is, but we should be able to solve that equation for b. So initially I'm going to go ahead and multiply both sides by b. Can't really solve for it while it's stuck in the denominator. So this gives us 6b equals 2 pi. And then to isolate the b, we'll divide both sides by 6. Okay, so in simplifying down here, again, the 6's go away. We get b on the left-hand side equals, a little simplifying down, pi over 3. Okay, so now our function looks like this. Y equals a cosecant of pi over 3 multiplied by x on the inside here plus d. Okay, next I'll go ahead and say, let's find a. A is going to be half of the total vertical distance. All right, not a nice way to say that, maybe. Half of the total vertical distance. If this was sine or cosine, we'd be calling it the amplitude. Basically, we want to look at where this lowest point is on this loop and where the highest point is on these other loops at the bottom. And we want to figure out that total vertical distance and then divide it by 2, take half of it. So in our case, we can make this a counting problem if we want, that we have 1 unit up above, and then we have 3 units down below. So that's total of 4. But remember, we want to take half of that. So A is going to work out to be 2. Again, maybe note that from our basic sketch of our cosecant graph, it starts at the top. It hasn't been flipped upside down or anything like that. I would say don't worry about a vertical transformation in this case. So let's just use A as positive 2. So in building this up, we're now at y equals 2 cosecant of pi over 3 times x plus d. And to find d, well, d is like the middle. If it was sine or cosine, again, we would call this the midline. Basically, if you draw a line that's exactly halfway in the middle of this graph, that's what we're looking for. So we can call this the average of the vertical distances. Maybe not distances, average of the vertical values. I don't know if that makes sense. All right. The vertical values that I'm talking about are, again, 1 and -3. So if we take their average, so 1 plus -3, divide by 2, that's going to be their average. What's that work out to be? -2 over 2 looks like -1. What this means on a graph is it's going to be subtracted from the entire function. So this means everything's been moved down 1 unit, which kind of makes sense on our graph, that if I draw a line going straight across here, that's 2 units from that loop. It's 2 units from this loop. All right, so it's everything's been shifted down 1 unit to make that line directly in the middle. So that gives us one of our solutions, y equals 2 cosecant of pi over 3 times x, and then to move it down 1, we do a subtracting 1 at the end. So that's a solution. There is an alternative solution or two that we could find if we want to use secant. So let's walk through that real quickly. Most of this information is going to be the exact same. Okay, as far as the period doesn't change, vertical shift didn't change. All right, so A, B, and D are all the exact same as what we just found. The only difference would be if we want to start in the middle, much like our secant graph does, it starts at this bottom point and goes up from there, has this middle loop, and then it would be kind of finishing up over here, back at the bottom. All right, so we could either think it's been shifted to the right. What is that, 1.5 to the right? Would be one option. Or we could say it starts over here. I'll put it over in orange. Starts here at the bottom, goes up, loop in the middle, and then ends right here. Okay, so in that case, we could think of this as moving to the left 4.5 units. So we have 2 options there, right? Either right 1.5 or left 4.5. So again, it goes 2. Secant is going to be we're changing the function around, right? Our b value goes here, and then we have an x minus c. And then -1. Remember, a, b, and d, all the exact same computations we just did for cosecant. Now, the difference is, we said we could either move to the right 1.5, or we can move to the left 4.5. All right, to accomplish either one of these, what we're going to do, I'll write them out here. We have y equals 2 secant of pi over 3, and then to the right 1.5. What we're going to end up doing is we're going to do the opposite of what we think it should be. It's kind of counterintuitive. So we're going to subtract 1.5 directly from x to move everything to the right. But if we want to move everything to the left, we have to add, which I know feels counterintuitive, but that's how it works. So that 4.5 gets connected directly to the x. We're going to add 4.5 to move everything to the left. So now we have 2 more equations here that would all give us that exact same graph that we had given to us from the very beginning. So I hope this helps out as you're working on these. They're really not horrible, but it takes a little bit of practice to get where all those pieces of information come from. So good luck as you're working through them.